So here, so these are member stiffness. So we just take away another plate. I'll just look at this one plate. Model compressed. So this is this member and this member, they are compressed members. And as if we model them as if they are thruster is the plural form of thruster, and spreading from the bolt head and not to the middle point. Okay? And so you can see we have a middle point. It's a middle point. Without loss of generality, we just denote the middle point. For this case here, so you can see each frustum and has a half apex angle of alpha. So that means this is the alpha, right? So you should know that this is alpha. And so this is very, very important, the parameter. So find the stiffness for frustum in the compression. And so we want to find the stiffness of this plate and also another plate. So there are several important this is parameters. This is the DW. So DW, so here is a washer. Okay, so this is a washer, the washer diameter. And we have this is a D value here is a bolt diameter. So this T is the thickness, and T is the thickness of the first plate, and the half L is the middle point between this is the bolt head and a nut. I want you guys to pay attention to what I say. There are a lot of very, very tiny parameters, but they are very, very important. So one more time, so DW is the washer diameter. So this lowercase d is the nominal diameter of this thread, and lowercase t is the thickness of this first plate, and the half L is the middle point between this L here is the distance between the washer and the nut. So that's the whole thing, everything that in between, and they are called L. So that means half L is the middle point between this is the bolt head and this the bolt and the nut. So here, so this is a capital D. Capital D is a washer. This is a capital D here, and so this is alpha is apex value usually, and it equals 30 degrees. Right now, guys. So half apex angle, and usually it equals 30 degrees. So that's a convention. Don't ask me why. Okay, so that is convention. So this is so x and dx, and so this is a lowercase d. Questions regarding this slide? Question regarding this so how can we get this? How can we derive the stiffness matrix? I'm not sorry, on stiffness of this is this member. Okay, so what I want to show you is that I'm supposed from here this is x, and here is a dx, and how can we do that? I'm going to show you this derivation. I will go show you a little bit on how can we get this is the k here, and this k is our final derivation, final step. It equals the load divided by the corresponding deflection. And how to get this deflection? So I want to get you to show you guys. And all you guys have learned the calculus 1, 2, 3, right? Okay, now so it is and how to calculate this? How to derive this one? P delta. Okay, suppose we have a P here, we have a P. So sigma, right? Sigma and equals P divided by A, and A is the cross-section area. So here, guys, you can see. So I have a load P here, this compressive load P. So this is a P equals the sigma, the stress, okay? The stress equals P divided by A. And I also know that for 1B, the epsilon is a strain. And strain equals and the sigma and divided by the Young's modulus. You guys agree? You guys agree, right? So epsilon equals sigma equals this one. So and we know that. Then we look at and this is infinitesimally small the segment delta x dx. Okay, just look at the dx. For this dx and what kind of the d this is e. Okay, e equals sigma multiplied by e and equals P divided by A, the Young's modulus. So what is the deflection? So this is for this dx. The dx is the length. So we know that d delta equals epsilon, right? And epsilon multiplied by my original x. You understand, guys? So this is the deflection of my dx. Here, you can see here. So this is infinitesimally small light segment. Right? So this gets deflection. The length and the deflection is totally different. The deflection equals the final length minus the original length. So dx is my original length. The deflection equals Young's equals your epsilon, the string multiplied by your delta x, right guys? Delta x is the original length. So we can just write this epsilon the dx. So delta x and dx is the same thing as long as it's very small. So delta d delta equals epsilon dx, and then we can have this equation. We just plug in and p and dx divided by an ae. So this is my d delta. Right? So this is my d delta only for that small light segment. And what is A? And what is A? Is a cross-sectional area. Is a cross-sectional area, guys. So you can see, okay, so keep in mind. So this is a hole. Keep in mind, guys. And here is the hole. Okay? Here's a hole. The effective cross-sectional area is, for example, for this end, is this part and this part. But keep in mind, this is a hole. As a result, and so this is equals pi the outer radius square minus the inner radius square. Inner radius square is the host diameter. So it says so this Ri equals and half d is the thread. Okay.
Okay, so we're assuming the member is like a circular cross section or a circular area with the hole in the middle.
Yeah,
Okay.
yeah. Circular. Yeah, you are right. So from here, so this is the front view. Okay, if you look at the top view, if you look from here, and that this is just like this is my outer diameter. So here is a hole. Okay, here is a hole. So here is the diameter. So this is the diameter of the thread. However, this is R. This is RO. It is changing. Okay, just a cone. As a cone. At the top is so big, but the bottom is so big. So this RO is changing, but this D is constant, and D equals 2 RI inner. So this is Ri is constant, D is constant. That is a thread. That is a D because this is the hole. So you can get this A here. Okay, after you get this A, and for this delta, for here you take the integrate this one on this side, and you can just go here and do some manipulation, and then get this delta. And then you know that I apply load, and then I know the corresponding delta, and this delta from 0 to t, the whole thickness, And so I can know what is the total delta for this member. As a result, I can calculate the stiffness K by dividing P using the delta. Okay, guys? So this is how we get this equation. And I will not test your understanding of this one, but if you know how to derive it, and you will have better understanding of how to calculate this K. You understand, guys? As I said, if you have learned this is calculus 1, 2, 3, and you should know how to do the integration. And the most challenging part is here. And how can we establish the relationship between delta and this is x? And the gap is bridged using the Ebers law. Because the deflection equals the strain multiplied by the original length. Right? Questions regarding this one? As I said, I will not test understanding, but so this is very, very useful step to reinforce your understanding of this is a final equation. The math is very useful. Even though math is very tedious for all the equations. I do not say this in front of the math professors. Questions? No questions? So this is you should understand not just use this one, you should know how to derive it. And then just alpha usually is 30 degrees, so this is a convention. Sometimes you can get a different value. However, you can get this the different value if you buy some customized. This is the boat. So this value, so all these values, D we know, lowercase d know, Young's modulus know, the pi know. This is the natural law until you can get a K. So this equation is 20. We can use this equation to get any thruster. And P is a stiffness. And then combine all thruster as a spring in series. Right? So we know that. So this is we have a bolt. This is a bolt and compress bolt and nut. These two guys and compress multiple the plates. And so these multiple plates they are arranged in series. So if we treat each of them as a spring, we can just think that we put multiple springs in series, and then we can use this equation to get this is the total effective Km. Km means the total effective stiffness for all members between the bolt head and nut. Question, guys? No question? So here are some observations. If the group consists of any number of members, all of the same material, and two identical thruster can be ended in series. Why? Because so this K is related to Young's modulus. Okay. However, if it's a two plates and they are made of different materials, that means and they have different Young's modulus, and that's another story. And how to do that? I'm going to show guys. So this dW is a water phase diameter. And using standard water phase diameter, which equals 1.d. So this Km can be simplified. So keep in mind, so this is for two plates that are made of the same material. You cannot use this equation for the case that you have two different materials on four plates. So IBM, okay, so you can use IBM to do these things, and so this is our analytical equations, and if sometimes it's so the case is very, very complex, and then we can use the finite element method abacus to build this is the model to get the member stiffness. So this aspect ratio B divided by L. Okay, so this is a aspect ratio. D is the diameter, L is the length. So that is a aspect ratio. So here is a dimensionless stiffness, and so this is a normalized one by divided by Young's modulus. And so do you guys have interest to do some abacus modeling?
Yes.
Okay, I give you a tool. If you want, I can give you another one. Okay. So here is a empirical equation. So this is Kn divided by Ed equals A exponential EdL, and A and B, and they are material parameters. And for different materials, they have different AB, and you can use this equation to compare this result, the results obtained using this equation, and with the results that you calculate using the equations. All right? Questions so far? So here is the example, guys. Here is the example. I want you guys to pay attention. So here, so I have a boat, I have water, and I have a knot. I put this boat, I use this boat to fasten two plates. So whether they are made of different materials or they are made of identical materials, and we will differentiate. We will talk about both. So here, two plates are clamped together. Water face is 1 inch. 1 inch UNI multiplied by 1/2 inch. This is the length as A grade 5 bolts, and each with a standard 1/2 it is steel plate this water. So we determine the member spring rate and spring rate. Okay, this is spring constant Km member. M is this member. If the top plate is a steel and bottom plate is spring cast iron. So for this one, it's a more general case. That means we have two different material, two plates that are made of two different materials. And then you say, I use the method of conical thruster, the same thing, and we just talked about conical thruster. Determine the member spring rate Km if both plates are steel. So this is a special case, and is a simplified version. And then we use this 8-23, and which 33 is this empirical one, and to determine the member spring rate Km if both plates are steel, and compare the results with part B. And so you can see the steel, okay? If we have steel here, and we can get A and B. If A and B is given, they are given, and D, we determine D, L, and ED. So using this equation, we can empirically get this Km. How close it is, how accurate it is. And we compare this one with our analytical equation, analytical solution. So finally, determine the bolt and spring rate and KB. This KB is for the bolt. So keep in mind, I want to emphasize, we have a KB and Km, and they are different. And KB is a stiffness for the bolt, and Km is a stiffness for the members. For the members, that means, and all these things that are located in between the bolt head and the knot, they are not bolt. Okay? Be very, very careful. And in our midterm, I give you the problem. I only ask you guys to calculate the KB. Is needed. And for all other things, you can just practice. Okay? Okay, and how to calculate this one? The first one, we have two different material. Whenever you see this and two different material, you must be paying more attention. Okay. Whenever you see the two different material, and what you need to do is that, and you get the midpoint, and between the head and the knot, get the midpoint, right? So then you draw a line, the midpoint line, and for this case, the midpoint line is on the second plate. This midpoint line is on the second plate. And you can see if we draw the midpoint line, and we will have, and this is a frustum. So this one is a first frustum. First frustum. Right? So this one will be the second one. Why I need to have the second one? The reason is that this part is made of one material. So this part is made of another material. And you cannot use one equation to accommodate a cone that contains two materials. Okay, guys? I need to be very, very careful. Otherwise, your answer will be totally wrong. And even though this calculation will not be required for our midterm 1, midterm 2. No. For our upcoming midterm, exam 2. So you need to know that, okay? So however, on the contrary, if I know this material and this material, they are made of identical material. And what I need to do is that I just need to find the midline. So this one will be one frustum. So this one will be the second frustum. So then I put them together. You understand? But however, now for the first question, if these two guys, one is made of steel, one is made of cast iron, I know that, and these two guys are made of two different materials. So first, get this is the midline, and then I know that so this part and this part they are different. We need to treat them as two different frustum. Understand, guys? And then for this case, we have this frustum. So this second frustum and the third frustum. And then we should have, I will just treat them as this is one spring, and so this second spring, and this is third spring. And then we calculate the Km by assemble on 3 springs in series. Question, guys? You need to be very, very careful, okay? And so here, the thickness, you can just get a table. The thickness usually, so this one, if I test your understanding, I will give you. I will not bother you guys to get the table. And this value, thickness of the washer is given. Thickness, give the thickness. Then for this is a figure here on the first halfway. Okay, you can need to get the halfway. And halfway and from the bolt head and to the knot. And how to get the halfway? And you need to put the thickness of washer, the thickness of first plate, and the thickness of second plate, and put them together and divide by 2. Right? So here it will be our midpoint. After we get this midpoint, and we will know. So yeah, another exception is that if the midpoint is exactly the same as the interface, and we will be lucky. Okay, we will be lucky. That means we only have the 2 plates, and we still have the 2 cones or 2 frustum. You understand, guys? So the reason here we have 3 frustum is that its midline is not identical as this interface one. Right? However, if this one, they are the same, that means this one plate and this one frustum, so this is second frustum. And then we can just simplify our problem. Questions so far? Questions, guys? No question? You guys are very smart. Now, so I will get it here, guys. And so I know this is a 0.75, and this is a 0.75. So also you need to calculate the gap between this line and this line, right? Because this is the thickness of the second frustum. So you need to calculate this one. And then what you need to calculate is, so this from here and to here. So this is needed because in the equation because we need to know the D, okay? So you can see this equation. So this D is a D, okay? So this D is the diameter on the top of the frustum is a D. And for here, okay, some students say, Doma, and why we just need this is a top diameter. And why we don't need this one. And we know that, so they are related. If we have D here, so if we have this angle, we also know the thickness, and then we can calculate the distance from this point and this point. You guys agree? So we only care about the diameter on the top, the smallest one. Suppose this is a trapezoid, we only take care of the distance on the top, the shorter one. And for the longer one, we can calculate because we know the relationship between this one and this one. This is alpha here, and also thickness is given. You have sense? And then we come back to this. So how to calculate 1.437x and how to calculate? As I said, okay, I know the distance from here to here. I also know here is a nice 30 degree. So this angle, if I draw a vertical line, so this angle is a 30 degree, right? Okay. And then if I know this distance, and then for here, so this is right angle. This right angle is 30 degree, and for this part I will know because I know here is the thickness. The thickness for this one is equals the thickness of this plate and the water thickness. Let me show you guys. Okay, so the distance between the joint point, so this is needed to calculate. We can get this is a gap. The top thrust consists of steel washer, steel plate, and this one in of the cast iron. So that means this one. And since water and top plates are both steel, water and top plates are both steel. Young's modulus. So this is Young's modulus. This is steel, and so this is steel. And they can be considered a single cluster of this one, okay, so this one we just consider the same, the steel, we can consider the same cluster. They can be considered as a single cluster of 0.59 in thickness. That means from here, and to here. And how to get this value? And you use this midpoint minus this. So outer diameter of the frosted of the steel member as a joint, so here's the joint, is 0.75, is 0.75 plus this. This is a 30 degree. Can you see? Can you see that? No? So this is a 30 degree. And so I know the thickness here, and so this is thickness T1 and equals, and this, right? The thickness equals 0.95, 0.595, the thickness. And I can calculate this value, right? Okay, so this x, suppose this x divided by T1 equals tangent theta. Equal tangent theta, sin theta equals tangent 30 degree. So I can get this x equals T1 multiplied by tangent 30 degree. So this is x. Okay? And you also I know this is a symmetric about this is the center line. So the total, guys, the total, I want you guys see me, right? Look at me. The total diameter, well, at this on this plane, and it will be equal to, and so this is 0.75 for here, right? So here, this is 0.75. So this is the diameter. If I this is symmetry, so this is also 30 degree. Now, from here to here, so this one and will be is suppose I will use this is a D, and D equals 0.75 and plus 2x. Right? So I have x here, and I have x here. And so this gives us 1.437. So this is my D and for here. So which equals is the D for my second frustum. So the outer diameter at the middle point, outer diameter at the middle point is 0.75 and plus this, the same thing. So now this time it is for the middle point. Middle point is, so this is this one is 0.725. So this one, and they are using the same equation, but the thickness is different. Okay? Okay? And then you can calculate the K1. And the K1 is for first thruster. On first thruster, and you use this value. So 820. Okay, let me show you the 820. So this is 820. So 820. So this is constant pi Young's modulus D, the D value. The D value for our case, for this case, this is our D value. As I said, a D value is the diameter of the smaller to the tall. If we have a trapezoid, right? Trapezoid, that's the diameter of the tall, the smaller side, parallel side, one of the parallel sides. So this is D 0.75. For this one, for the second, the thruster, and this case D, okay, and will be equal to this distance, and which equals to this one. So, but that will be the cast iron, is another material. So you can see upper cast iron thruster here, it equals 1.437. So this value. Are you guys following me? So this is very, also it's very, tedious. A lot of details here, right? Okay.
Could you just like explain what a frusta is again? Like just like the fundamental, like what is a frusta?
Frost is a cone. Okay, frost is the cone. It's just like a cone. We cut it the top and cut the bottom, and we just show it in the middle. We can show. I can show you. It's a cone. It's a cone. We just cut the top and cut the bottom. So this one, this face and this face, they are parallel to each other. Okay? Because it's axisymmetric, okay? So we have a bolt and we have multiple plates. So that is not axisymmetric. Along this is the center of the
Well, the
bolt.
weather is looking.
So this is the cone. So this is the cone. So D, we are using the capital D value. Capital D value is actually this is our capital D value. The smaller, the diameter of the smaller one for the cone. So this is our K1 and K2, as I said, K2 we use, so this one is our capital D in the equation is a K2. And for the K3 here, guys, and for K3, the D is from here to here. So this is K3 for lowercase, and K3 is 0.75. So you can see this from here to here, and from here to here, they are identical. What? Understand, guys? I want you guys to take a close look at this one. And even though for our midterm, I only test your understanding how to calculate the KB, but how to calculate the KM and will be very useful, not just for machine design course, very useful for your future job, future career. So you put the three guys together using this equation, you can calculate the KM. And keep in mind, and KM means the member stiffness. KB is the bolt stiffness. Question so far? No question? So for the if these two guys they are made of steel and they will be easier, okay? They will be easier and you can just using simplified version. And for C, that means we use the empirical equation, and because it's steel, and based on that table, we can get the corresponding A, corresponding B, and using this equation, you can calculate the Km. As you can see, this Km analytical solution and this is empirical solution, and they are very close. You can see these two guys are very close. And so last one, and how to calculate the bolt, and this is bolt stiffness. And bolt stiffness, so here is bolt stiffness. So how to calculate bolt stiffness? So this value is AD, right? The first value is AD, and second value is AT, and third value is Young's modulus. So this AD multiplied by this is a threaded force. I'm sorry, this is a threaded length, and so this is AT multiplied by unthreaded length. They just switch. Questions so far? So you need to calculate the LT, the total length. You need to calculate LD. LD is the unthreaded length. This is LT is a threaded length in the graph, and you can get using this equation, and then you can calculate this one. AD can be calculated AT, you need to check the table. And usually if I test you understand of this one, and usually AT is given. And then you use this. Okay, we're almost here. Let me summarize this one a little bit. First one is, okay, first one, if you have the two plates without loss of generality, and you need to figure out whether these two guys are made of same material or no. The first thing. And second thing is that you need to calculate the midline, where the midline is. Right? So this is most important. If you mess this up, the following calculations will be totally wrong. So these are two most important things. First, whether these two guys are made of same material or this is the first one. Second one, and calculate the midline. Make sure the calculation of midline is correct. And then use this trigonometry. Use this trigonometry. If I know this length, if I know 30 degree, imaginally is a 30 degree, I can know. So my bottom line. So this is the top line. My bottom line is length because 30 degree. A thickness given, I can calculate this capital D. So this capital D is used for the second thrust.